That is so random. No, it's really not. Most of the time when people say that, they don't know what they're talking about. True randomness means equally likely. Equally likely doesn't sound truly random, but when we think of all the possible outcomes, when we say equally likely, and we kind of consider all possible outcomes, we'll explain what we mean by that. But if someone tells you they were just thinking about you and that's so random, well, really not. You're one of the few people they know, and out of the billions of people on this earth, so it's probably more likely that they would be thinking of you than anything else. And okay, a random experiment is an experiment where you do not get, or you do not necessarily get, the same outcome. You don't necessarily get the same outcome if the experiment is repeated under identical conditions. As identical as we can make them, like tossing a coin or things like that. So, that's one that we can kind of refer to: a coin toss, a card deal. These are the games that we like to talk about when we refer to chapters on probability, because we kind of rely on the randomness of this, and those are truly random. We hope that when we deal cards, you could get one out of any 52 possible cards in the deck, and they're equally likely. Otherwise, something's wrong. So when we start looking at this, we have to define a few terms, and these are terms you need to know. So we're going to highlight the definitions you need. Oh, you know what? They're already in bold, so I'm just going to be highlighting things I already put in bold. But okay, a sample space is what can happen. A sample space is the set of all possible outcomes. Meaning, as an example, if two coins are tossed, then the sample space is, it could be heads, heads, it could be heads, tails, it could be tails, heads, or it could be tails, tails. And the sample space contains 4 possible events, but one of those 4 must occur. Now, what does occur, or what could happen, or what we want to happen, is another way to say this, is a subset of this. An event is a subset of the sample space. So if I'm looking at an event, I could say the event of at least 1 heads. So that would be to kind of go up down here and just pull the ones that have at least 1 heads. Heads, 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 tails, or tails, heads, but not tails, tails. So those definitions of a sample space, a random experiment, and an event, you must know. Now, I found these images and I thought they were kind of cool. Here's the 52 possibilities of a card, and here's the outcomes of rolling 2 die down, 2 regular ordinary die. If you look at how many possibilities there are, here's 36 possibilities, and here's 52 cards. 36 should make sense because there are 6 times 6 possibilities for any blue, white, and black die, or however they're doing it here. So if we refer to that, we're going to roll 2 dice, and we're going to express these as ordered pairs, like rolling a 6 and then a 1. We're going to express as 6, 1, first, second. So we're going to specify the event that the sum of the numbers is 7. And let me go back up here. This is actually the sample space. So I'm actually going to look to see what are all the ones where the sum is 7. Well, we could kind of list them in order. If the first one's a 1, then the second one would have to be a 6. If the first one's a 2, the second one would have to be a 5. 3, 4, 4, 3, 5, 2, 6, 1. And those are all the possibilities where the sum of the numbers is 7. And you could put those in any order. Set notation does not necessarily denote order or need an order. So, next, if we specify the event that the first die shows a 4, well, then we're just going to list all the possibilities where it's 4. 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. There's 6 of them. This one's a big one. Specify the event that your die are not consecutive numbers. And I put this down because I want you to be sure that you can list appropriately. So we'll start with 1. If they're not consecutive numbers, 1 can't be 2, but it could be 1. It could be 1, 3, 1, 4, 1, 5, or 1, 6. And this is an ordered way to kind of make sure that we've listed them all. And then we're going to do 2. Couldn't be 2, 1, but it could be 2, 2. Can't be 2, 3, but it could be 2, 4, 2, 5, and 2, 6. I could go 3, 1, but not 3, 2. I could go 3, 3, but not 3, 4. I could go 3, 5, 3, 6, 4, 1, 4, 2, 4, 4, 4, 6, 5, 1, 5, 2, 5, 3, and 5, 5, and 5, not 5, 6. And then we have finally 6, 1, 6, 2, 6, 3, 6, 4, skip 6, 5, but then last one would be 6, 6. So there's a lot of possibilities there, but I made sure that I kind of hit up all the ones that are not consecutive numbers. Okay, next one, draw 1 marble from each box. If I specify the sample space, I can just do these with letters. These represent colors. If you can't see this, blue, red, this is blue, this is red, this is green, and this is yellow. So the sample space, if I draw 1 from each box, it could be blue, 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 yellow, blue, green, or blue, red, or red, blue, red, 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 yellow, and red, green. And then if I specify the event that 1 marble is blue, well, it could be blue. And see, the question is actually you're going to have to ask, does it need to be 1 marble only? 1 marble is blue. Let's say at least 1 marble is blue, because really you should say at least or exactly 1 marble is blue to clarify what you're talking about. If it's at least 1 marble is blue, this would be, this case, blue, 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 yellow, blue, green, blue, red, and then red, blue. And that would be the one where, I know you guys hate it when I do this, so sorry. That would be the at least. And then if it's exactly 1 marble, then we have to kill the blue, blue possibility. And just put blue, yellow, blue, green, blue, red, or red, blue. We've gone to the pound to adopt a puppy. Is that a pound? I don't know what that is. You'd like a beagle or a cocker spaniel that is brown or black and has either a white tail or brown tail. So you've got some cases. How many possible puppies fit your criteria? Well, we have 2 possibilities for the breed, 2 possibilities for the color, and 2 possibilities for the tail. So 2 times 2 times 2 is 8, and if I list all of them, I could say, let's see, let's label these with some letters. We'll call this G and C, and then brown would be R, and black will be L. I'm not using the B. And then white would be W, and brown, we can use B there. Okay. And then, so if I just kind of list all these possibilities, I could have G. If we start with a G, then it has to be G, R, W, or G, R, B. I could also do G, L, W, or G, L, B. Then I could do C, R, W, or C, R, B, or CLW, or CLB, and that's all the possibilities. It's very common to assign letters to possibilities like this, and you'll see this a lot of times in genetics, which I'm very, very much resisting bringing the biology in here. But okay, now we get to probability. So if you want to pause this and take a break, and we're back. How randomness leads to probability. Well, if you have a sample space containing n equally likely outcomes, and that's what all these a sub 1, a sub 2, a sub 3 to a sub n means, then the probability, which is a measurement of how likely something is to occur, the probability of each simple event or simple outcome is 1 over n. And that should make sense. If you have 4 equally likely outcomes, then the probability is 1/4. If the sample space consists, should be an S there, I'm fixing your file, consists of n equally likely outcomes, and if k of them are in event E, then what we say is the probability of event E, the probability is 1 over n plus 1 over n plus 1 over n, all the way with k of them, which is equal to k over n. So that means that if you have 4 things out of like 10 things you want to happen, then the probability is 4/10, which can be reduced to 2/5. And we'll see this happen, so don't get so hung up on this. What I really want you to have the memorized definition here is that of probability, what probability is. If you listened very closely, I did verbally give you a definition. We'll see how much you write instead of just kind of a copy. Number 4, a spinner is divided into 10 digits. I'm not going to try to draw a spinner with 10 digits. Okay, I'm going to try. 1, 2, 3, 4, 5. There's 10 digits. And the spinner must land on a digit. What is the probability that the number is 4? Well, we're going to assume that all of these are equally likely and that it's evenly placed. Oops. So, just making sure it's still recording. We're going to go back to probability that it's the number 4 would just be 1/10, right? Because there's 1 4 and there are 10 possibilities. That's not that hard. Probability that it's between 0 and 25, well, all 10 possibilities are between 0 and 25, so that's 10/10, and the probability is 1. The probability that it's a multiple of 3, well, I could list the event, and that would be 3, 6, or 9, so there's 3 possibilities out of the 10 total. And then the probability that you get 1/2, well, that would be 0, because there is no 1/2 among the 10 digits. Is it that easy? Well, right now it is, but don't worry, we'll make it more difficult. Let's move on to the next one. Got a bag containing 8 brown socks and 6 black socks, and it's dark, and you don't know what socks you're putting on, so you're just going to pick them randomly. It's the probability that they match. Ignore the fact that you probably should know what kind of shoes you're picking with these. The probability that they match goes back to kind of the very, very big definition of probability. And so I'm going to throw a definition of probability down, one of mine, which is the number of ways the event can occur. Number of ways the event can occur over the number of ways anything can occur. So here's another definition of probability. I like this definition because it really makes me think about what it's doing. It also means that when we talk about number of ways, we can use a permutation or a combination, depending on how we're doing it. Like if we're picking socks out of a bag, we don't want to use a permutation. We don't care what order they come in. We just want socks. So the number of ways the event can occur. Well, if my event is 2 brown socks, then the number of ways that I can have 2 brown socks, well, I have 8 brown socks total, and I'm going to choose 2 of them. Now, if I say my event is 2 brown socks or 2 black socks, we say, well, 2 brown socks or 2 black socks, those are mutually exclusive. Mutually exclusive. You might want to write mutually exclusive because you'll not remember what that is. Mutually exclusive because can't happen at the same time. You can't have 2 brown socks and 2 black socks at the same time. Can't happen at the same time. So I'm going to add 6 choose 2 to represent the black socks. I'm going to put that over the number of ways anything can occur. Well, there are 14 total socks, and choose 2 of them. So this is actually a calculation that's going to give me the probability. And if I do this in my little hand-done way, 8 times 7 over 2 times 1 plus 6 times 5 over 2 times 1 over 14 times 13 over 2 times 1, you get, this would be 28 plus 3 times 5 is 15 over and 7 times 13 is 91. 25 plus 15 is 43 over 91. You actually have less than a 1/2 chance of doing this. 43 91sts. Interesting. Number 6, in many variants of poker, 7 cards are dealt from which you try to make your best 5-card poker hand. This is Texas Hold'em, and this is many other variants of this. What is the probability of a flush with only 5 cards of the same suit? Well, what I mean by that is if we have 7 cards, and I kind of wrote this here, I want 5 cards to be all the same suit, and then the other cards to be different. So let's start this. How many cards are there of this one suit? Well, there's 13. Choose 5 to get 5 cards of the same suit. So that's the number of ways of getting 5 cards of the same suit. Then I have times the remaining 39 cards. Choose 2 to get 2 cards of different suits. But as you saw in the homework on combinations, we're also going to have to do a times 4 because this could be any suit. We had to do that a few times when we talked about cards of the same suit. So the difference between this and the previous homework is that now we're going to divide this by the total number of ways to get any 7 cards, which is 59, choose 7. Now, for ones like this, it's going to be acceptable to use your calculator. This is why we let you use your calculator. And if I look at what an answer is, I'm just going to do one of these things. And we'll stick that there. Okay, next, 5-card flush. This is a 5-card where we could have any of the possibilities. What I mean by that is 5-card flush could be 5 cards of the same suit, could be 6 cards, could be 7 cards. All we need is just 5 cards in the same suit. So I'm going to say could have more than 5 cards of the same suit. Remember, we're dealing you 7 cards. So we're going to take the original thing here, this, and we're going to copy paste it down here, which, laugh it up, one day you guys will be able to do that. And then I won't hear people whining when I do that. Okay. Then we're going to do the 6-card case. So you guys should kind of reason through. We're now going to take 13, choose 6, plus 39, choose 1 times 4 over 52, choose 7. And then finally we're going to take 13, choose 7, and then I don't really need to worry about the 39, choose 0, because that's ridiculous, times 4 over 52, choose 7. Again, this is the 6 cards in the same suit. This is the 7 cards in the same suit. And we're adding because they're all mutually exclusive. They can't all happen at the same time. Oh, I should not add right there, though. That's multiply. Glad I caught that. Some of you are probably wondering about that. Okay. Now I'm going to pause while I enter this in. This is going to take a bit of time for me. And this is what I end up with. Not as many as I thought I would have. Again, I'll just grab that and put it there. Okay, there we go. Next. Find the probability that the dart thrown inside the given target will hit the shaded region. Assume the dart is equally likely to hit any point inside the target. The target and the regions within are either squares or circles. So I want it to hit this thing. So basically I need to find the area of the shaded, which is equal to the area of the circle minus the area of the square. So the area of the shaded is equal to, circle is radius of 5, so 25 pi. You guys should know that the area of the circle is pi r squared, minus, and you should know the area of a square is 64. So I have 25 pi minus 64, and I'm actually going to say the probability is the area of the shaded over the area of the whole. So if I go area of the shaded, 25 pi minus 64, I'm just going to put that right here, over the area of the whole would just be 25 pi. And that would be the kind of exact answer. If I wanted to approximate that, I could plug it in, so I'll pause it again. And I get approximately 0.185, which is about a little bit less than 1/5. So your odds of just randomly throwing and hitting that shaded, not very good. Of course, you probably wouldn't be so random, you'd be trying to aim for the shaded. If I do that here, we're just going to do area of the smaller one, which is 6 squared, over area of the larger one, which is 10 squared, which is 36 1/100ths, or 9/25ths. Lastly, some simple questions. The probability of randomly choosing the number 5 out of any natural number from 1 to 100. Well, there are 5 natural numbers, or 100 natural numbers. So that's 5. Nope, just kidding. 1 over 100. That's what I was trying to catch you on. There's only one number 5, so you got 1/100th. The probability of randomly choosing the number 5 out of any real number. Well, there's 1 5, but how many real numbers are there from 1 to 100? How many real numbers? There are infinitely many. And 1 divided by infinity is about as impossible as 1 divided by 0. So I can't really say that. And just for a hint of what's to come, what I can say is the limit as x approaches infinity of 1 over x. Basically, I'm trying to say, well, as x really gets large, and if x gets crazy large, what happens to 1 over x? That is actually equal to 0. So for our practical purposes, we can say 1 over infinity is equal to 0. You can actually even say 1 over 0 is equal to infinity in some cases. But the probability of randomly choosing the number 5 is 0. You will not do it. Let's think of that one for a while. Goodbye.